Water and wastewater infrastructure is often described as an ideal environment for artificial intelligence. The systems are instrumented. They produce continuous signals. They contain interacting physical, chemical, hydraulic, and electrical processes. They also operate under changing conditions, where a small change in flow, loading, equipment availability, or data quality can change the meaning of a measurement. That combination creates an opportunity, but it also creates a responsibility. A model can identify patterns in historical data. An analytics system can organize information that would otherwise be difficult to review. A control strategy can support more timely decisions. None of those capabilities removes the need for process knowledge, engineering judgment, or accountable human oversight. The United States Environmental Protection Agency describes smart sewer technologies in terms of real-time monitoring, modeling, analytics, and artificial intelligence or machine learning that can be aligned with the size of a facility and its objectives. That description is important because it puts the technology inside an operational system. Smart is not a single product, and it is not a guarantee of performance. It is a coordinated arrangement of measurements, communications, models, decision support, and people. In this episode, we will build that arrangement from the ground up. We will look at the data layer, the relationship between a physical process and its digital representation, the promise and limitations of advanced control, the governance of trustworthy AI, and the cybersecurity conditions that surround critical water and wastewater infrastructure. The central idea is simple. Intelligence is useful only when it remains connected to reality, bounded by safety, and accountable to the people responsible for the process. A useful way to understand intelligent infrastructure is to view it as a set of layers rather than as an algorithm. The first layer is the physical process: channels, tanks, pumps, treatment stages, electrical equipment, and the surrounding environment. The second layer is measurement. Instruments and other data sources provide observations of what the process is doing. The third layer is data acquisition and operational visibility. In a conventional facility, SCADA and related systems help bring signals into a form that operators and engineers can review. The fourth layer is modeling. A model represents selected relationships in the process. It may be used to explore behavior, support forecasting, or compare possible decisions. The fifth layer is analytics, which can help identify trends, anomalies, or relationships in the available information. Artificial intelligence and machine learning can be part of that analytical layer, but they remain dependent on the data and assumptions around them. The final layer is the human interface: the screen, report, alarm context, review process, or decision support workflow through which people interpret the information. This sequence matters because a sophisticated upper layer cannot repair a weak lower layer. If measurements are incomplete, poorly understood, or unstable, the model and analytics inherit those weaknesses. Smart sewer technologies can be adapted to facility size and objectives. That means the right architecture for one facility may not be the right architecture for another. A system designed for visibility and decision support is not automatically equivalent to a system that influences control. A system that works under one operating envelope is not automatically reliable under another. For professional teams, the first question should therefore not be, which AI tool should we buy? The first questions are, what decision are we trying to improve? Which observations are needed? What conditions make those observations meaningful? Who reviews the result? What happens when the data are missing or contradictory? And what authority, if any, does the system have? These questions keep the technology connected to the process instead of allowing the process to be redesigned around a software claim. Advanced control is often presented as the point where analytics become action. That transition deserves careful engineering attention. The Environmental Protection Agency identifies real-time control and decision support among the use cases associated with smart sewer technologies, while also emphasizing that design, cost, and return can differ among facilities. This variability is not a footnote. Water and wastewater assets differ in physical configuration, measurement coverage, process objectives, equipment condition, operating history, and organizational capability. A control approach that is appropriate for one arrangement may be inappropriate for another. Even within one facility, the relationship between inputs and outcomes may change as conditions change. For that reason, Advanced control should be discussed as a managed capability rather than an automatic upgrade. The engineering team must understand the intended objective, the signals on which the strategy depends, the range of conditions in which it has been evaluated, and the way people can review or reject its recommendations. The system must also have a defined response when data become unavailable, contradictory, or outside the model's known range. The model does not replace process balances. It does not replace safety limits. It does not replace the operator. Those boundaries provide a useful language for project reviews. A successful demonstration under selected conditions should not be presented as a universal design recommendation. A reported benefit should not be generalized beyond the facility, data, and operating conditions that produced it. The most credible claim for advanced control is therefore disciplined. It may help teams see, compare, and respond more effectively when the underlying data, model, governance, and fallback arrangements are suitable. The claim should become stronger only as evidence is collected within the relevant context. If AI is used in critical infrastructure, technical performance is only one part of trust. The NIST AI Risk Management Framework provides a voluntary framework for incorporating trustworthiness into the design, use, and evaluation of AI systems. For a water or wastewater engineering team, that idea can be translated into a practical governance conversation. The first element is governance. Who owns the system? Who approves its use? Who defines acceptable conditions? And who is accountable for decisions influenced by it? The second is measurement. How is performance evaluated? What evidence is retained? And how are errors or unexpected outputs recorded? The third is management. How are changes to the model, data, interfaces, and access pathways reviewed? The fourth is human review. Where does a qualified person examine the result? And what authority do they have to pause, reject, or escalate it? These questions are especially important because a model can be statistically persuasive and still be operationally unsuitable. A neat visualization may hide missing data. A stable historical pattern may not survive a new condition. An automated recommendation may be difficult to explain after the fact. Trustworthy use does not mean that the system is never wrong. It means the organization understands how it can be wrong and has a process for detecting, documenting, and responding to that situation. Human accountability is not a ceremonial approval step. It is a design feature. The operator interface should communicate enough context for review. The documentation should describe the model's intended use and limitations. The organization should know how to preserve a decision tree. The system should be evaluated not only during a successful demonstration, but also during degraded data, unusual conditions, and recovery. In that sense, governance is part of control performance. Without governance, an advanced control project can become technically impressive, but operationally ambiguous later. With governance, the same technology can be placed inside a clearer chain of authority.
Water and wastewater systems are critical infrastructure. CISA emphasizes that disruption of digital water or wastewater systems can affect communities and other critical infrastructure. This makes cybersecurity inseparable from the discussion of AI and advanced control. An intelligent layer increases the importance of boundaries. Operational networks must be separated appropriately. Remote access must be protected. Commands must be documented. Recovery must be tested. These are not optional details to be added after a model has been connected. They shape whether the overall system remains resilient when a component, connection, account, or data source is compromised or unavailable. The phrase safe fallback is useful because it forces a concrete question. What does the process do when the digital layer cannot be trusted? A fallback is not merely a password or a backup file. It is the facility's ability to maintain accountable operation when analytics, communications, or model outputs are degraded. The exact arrangement is facility-specific and should be developed by qualified teams. This episode does not prescribe a live operating procedure. Access protection also has a governance dimension. The organization should be able to identify who may view, change, approve, or execute functions. The command trail should support later review. Recovery should be more than a written assumption. It should be exercised in a controlled and documented manner appropriate to the facility. Cybersecurity and process safety should therefore be discussed together. The issue is not only whether an algorithm is accurate.
The issue is whether the complete digital pathway, from data source to human decision, and any authorized control influence, remains bounded, auditable, and recoverable. Every model has a relationship with its evidence. The relationship may be strong within a defined operating range and weak outside it. Three conditions are central for model reliability: calibration quality, data completeness, and stability of operating conditions. Calibration quality asks whether the digital representation has been aligned with the physical process in a meaningful way. Data completeness asks whether the evidence required by the model is present and usable. Stability asks whether the conditions that shaped the model remain sufficiently comparable over time. These are not abstract concerns. They determine how much confidence a team should place in an output. The correct response to uncertainty is not to hide it. It is to make it visible and to connect it to decision authority. A result produced during missing data or unusual conditions should be treated differently from a result supported by complete data within an evaluated range. A model update should be treated as a managed change, not as an invisible software refresh. This is why the research brief rejects broad claims that a model replaces operational balances, safety limits, or the operator. It also rejects turning a laboratory or experimental result into a general design recommendation without stating scope and limitations. Those rules protect both engineering quality and professional communications. For engineers and technicians, every impressive result must be accompanied by the conditions that made it possible. Every limitation should be stated before the viewer is invited to generalize, and every proposed use should identify the human role that remains responsible. A professional evaluation can be organized around 5 connected questions. First, what decision or operational understanding is the system intended to support? Second, what data are needed and how will their condition be recognized? Third, what does the model represent? Where has it been evaluated and where does it not apply? Fourth, what governance, review, and documentation surround the output? Fifth, how does the facility remain safe and accountable when the digital layer is unavailable or uncertain? This framework does not rank one technology above another. It helps teams compare proposals without confusing sophistication with suitability. A responsible evaluation should avoid presenting a generic savings figure as an expected outcome. It should describe the facility-specific objective, evidence, dependencies, and risks. The framework also creates a bridge between technical and organizational teams. Instrumentation specialists can discuss data condition. Process engineers can discuss physical meaning. Automation teams can discuss boundaries and recovery. Cybersecurity teams can discuss segmentation and access. Operations leaders can define authority and review. The model becomes one part of a shared engineering system rather than an isolated innovation project. Artificial intelligence, digital twins, and advanced control can contribute to a more informed view of water and wastewater infrastructure. Their value is conditional. The condition is engineering discipline. Data must be understood. Models must be calibrated and bounded. Operating conditions must be considered. Governance must define authority and review. Cybersecurity must protect a digital pathway. Recovery must be tested. And the operator, process balances, and safety limits must remain part of the system. The most credible future is not one in which the facility disappears behind an algorithm. It is one in which digital tools make the physical process more visible, make uncertainty more discussable, and help qualified people make better informed decisions without transferring accountability to software. For engineers and technicians, that is the standard worth carrying into every project. Intelligent infrastructure should be useful, explainable within its intended scope, secure, recoverable, and honest about limitations.
Its limits. Before a digital twin or advanced control initiative moves beyond a pilot, the engineering team should be able to explain the intended operational question in plain language. It should identify the data dependencies, the model boundaries, the review authority, the cybersecurity assumptions, and the recovery expectations. This is not administrative overhead. It is the evidence that connects a digital capability to accountable infrastructure practice. A useful pilot does not have to prove every future benefit. It should demonstrate whether the information flow is understandable, whether the output remains meaningful under realistic conditions, whether operators and engineers can challenge the result, and whether the organization can recover safely when the digital layer is absent or uncertain.
Documentation matters because the team that commissions a system is not always the team that operates it several years later. The same discipline improves communication with decision makers. Rather than leading with an algorithm label or a generic efficiency promise, an engineering proposal can state the operational purpose, the evidence needed, the conditions that limit interpretation, and the governance required to use the output responsibly. That makes benefits easier to evaluate and risks easier to discuss. In water and wastewater infrastructure, the physical process remains the reference point. The purpose of a model, a dashboard, or a digital twin is to improve visibility and support judgment within an approved scope. The value of intelligence is not that it removes responsibility. The value is that it helps qualified people recognize what they know, what they do not know, and what must be verified before action is taken.